Okay, great. So we have Nikolay, who is going to tell us about a compendium of logarithmic corrections in ADS-CFT.
Thanks a lot. Unlike most speakers, I will not start by thanking all organizers, but I plan to end in this way, so bear with me. Okay, I'm going to tell you about work I did, which appeared in this paper, and then hopefully will appear in the future too. It was done with these amazing people. Two of them, Marina and Suao, were at this conference, and the two others were not. Okay, so why we're doing what we're doing? Well, we want to explore this amazing identity, z is equal to z. On the left-hand side, you have the path integral with some specific sources of some CFTs, or a special kind of CFTs, and on the right-hand side is supposedly the path integral string theory or M theory, and the claim is that these two things are equal. And in recent years, as we have also heard, there are some tools to compute the left-hand side here. And so the idea is to use these tools and compute this as best as we can and try to learn something about string and M theory. Specifically here, I will talk about subleading terms in the large N expansion on the left-hand side and how can they be obtained from the right-hand side. And this is interesting because, as we heard from some speakers, string theory on ADS is not easy. And so we would like to find some tools to learn more about that. And M theory, we really don't know what it is, so we also would like some tools to learn about that. And some people here also care about black holes, so this thing on the right-hand side should know something about black holes, so this is a tool to study that. Okay, all of these are lofty goals, and in this talk I will be quite specific. I will work with 3D superconformal field theories at large N, and these things will have ADS4 duals in M theory. And more specifically, I will be interested in these log n terms, log n terms which appear in this large N expansion of the left-hand side here of this Z. Okay, here's the plan of the talk. I will tell you very, very briefly how to compute path integrals using supersymmetric localization. Then I'll move on to the bulk ADS4 side and try to explain how you can compute these log n terms from the bulk using some tricks. Then I will explain what Central European novels have to do with all of this. And finally, I will talk about how to... So all of these tools, or many of these tools, rely on supersymmetry, but we actually found a way to compute some non-SUSY observables using these tools, which is kind of interesting. And then I'll finish off by thanking the organizers. Okay, good. So many people worked on this. Here's a list of papers which contain the results I'm going to show you. The model we're going to look at is this well-known ABGM theory, which used to be called in some instances Bagger-Lambert theory. It's UN times UN Chern-Simons theory, and it has a bifundamental chiral multiplets, so it's a 3D n equals to 2 kind of notation here, but the theory has n equals to 6 SUSY. K is the Chern-Simons level, and the global symmetry when K is more than 2 is this SU4R symmetry, and then there's a global U1 flavor symmetry of sorts. And the claim to fame of this model is that it should capture the low energy dynamics of n and 2 branes on this specific orbifold singularity, C4 mod zk. Okay, I'll be interested in the large n limit, and a very specific one. I will keep K fixed and take n to be large. And in this limit, the dual should be this famous ADS4 times S7 mod zk solution. Here the zk, it looks like it's an orbifold, but it's actually a smooth space, kind of like a lens space. And using this tool of supersymmetric localization, one can compute various large N observables on compact manifolds of this model. Okay. Good. And you should interrupt me if you have any questions, complaints, compliments. Okay, good. So here's an answer. I'm not explaining how this was obtained, but I'm just giving you an answer here. So this is the path integral of the model on S3. N and K, I've already told you what they are. MA are things that are called real masses. So these are certain mass terms that are compatible with supersymmetry that you can add to the theory. B is a squashing of the sphere. So the metric on the sphere can be deformed in a way compatible with supersymmetry, keeping U1 times U1 invariance, and this B is the magnitude of the squashing. And on the right-hand side, you see an explicit answer that resums the 1 over n expansion. So this thing on the right-hand side is analytically known to all orders in 1 over n, and what is not known explicitly are these exponentially suppressed terms. Okay? And these B and C here are certain combinations of these masses and squashings. Okay? So if you are a large n person, you would like to expand this at large n, which is easy to do, because this is an Airy function, which is a known function. And at large n, there's this famous n to the 3/2 scaling, which at some point was a mystery of science, but we now understand. And then there's an infinite series of 1 over n corrections. Okay? The leading term here should be captured by ordinary two-derivative supergravity. The first subleading term should be some higher derivative term, and the focus of this talk is this log n term, which is in red. Okay? And what I want you to remember from this slide is that these B and C and all this whole thing is somewhat involved function of these continuous parameters M, M1, 2, 3, and B, but the coefficient of the log n term is just a simple rational number. So this is an interesting structure that we'll try to get some mileage out of and explain a little bit. Okay, so we can keep on going. You can change the manifold. For instance, you can put the theory on a circle times a Riemann surface. Even though apparently odd dimensions are bad, according to Shlomo, I'm doing this freely here, and I'm getting some mileage out of this. So here, I want to keep a certain amount of supersymmetry so that I can compute something. And the way to do it is to follow Witten and do a twist of the theory on the Riemann surface. I'm assuming here a smooth genus G Riemann surface, compact. And then the path integral of this thing can be computed, as we heard from Cyril yesterday. I'm not explaining any of this, but the result is an expression that at large n looks like this. We know this to all orders in 1 over n. And this is again a function of some of discrete fluxes of the flavor symmetry on the Riemann surface, as well as continuous parameters, very much analogous to these m's which I had before. And again, what happens is that the coefficient of the log n term is some simple rational number that is fixed by the genus of the Riemann surface, by the manifold. The claim to fame of this object is that it is an index, or a path integral, which knows about extremal supersymmetric Reisner-Nordstrom black holes in ADS. So these n's are the charges of the black hole, and so on. So this leading term is the leading A over 4 entropy of the black hole, and this is an infinite series of G Newton corrections to that. Okay? There's also the superconformal index, which is an object that we heard about from Shlomo. But now on S1 times S2 instead of S1 times S3, omega is fugacity for the angular momentum on S2. And again, there's some matrix model underlying this, which is much harder than this one. But again, using some tricks, you can compute this to all orders in 1 over n in a certain limit of small omega. And again, what happens is that these functions in front, which I'm not spelling out, but can be found in the papers, are functions of a continuous parameter, but the coefficient of the log n term is a simple rational number. And this index knows about the entropy of SUSY rotating black holes in ADS. So this is for the Rastak-Nordstrom black hole, and this one is for the Kerr-Newman black hole. Okay, so this is all I wanted to say about the QFT results at large N. Are there any questions? No? Everyone happy or asleep? Okay. Good. So we want to go to the bulk ADS and try to learn how to compute this log n term. That's the homework assignment. And luckily we had a good teacher, Ashok Sen, who told us that in the context of asymptotically flat black holes, which is what he was studying, you can compute the coefficient of the log area over G Newton correction to the entropy of a black hole by studying essentially free fields on a fixed black hole background. Okay? So the reason this is a reliable analysis, which he called IR window into the UV physics, so you can do a purely EFT analysis in the low energy GR limit and capture some information, the coefficient of the log term, which should also be obtainable microscopically. The reason that this works is this scaling limit, which you should use in an essential way, that the area of the black hole is much bigger than G Newton, meaning that this is some kind of a controlled semi-classical approximation. And here I'm giving you this as 0 for the Schwarzschild asymptotically flat solution, on which, so your EFT is GR plus NS fields, minimally coupled, of spin S, up to 3/2. And this answer, as you see here, is again some simple rational number. Okay? So we want to do kind of the same thing in ADS. And again, I'm reminding you what we're after. We have some asymptotically ADS4 solutions in which the scale of ADS is much bigger than G Newton. So this will be somehow the analogous scaling limit which he had here, where he used the area of the black hole, because he didn't have a cosmological constant, but we do have one here. And then we'll be chasing these logs here, which are again simple numbers. Okay. How does this work? Very, very briefly, you want to take all your light fields. So I'm imagining here some 4D effective theory of gravity with negative lambda, cosmological constant. I'm sorry, lambda here is not cosmological constant, so lambda is the cutoff scale, 1 over L is the cosmological constant. And then I have to collect all the fields with mass smaller than lambda, all the fields in my EFT, and compute the contribution to the path integral. But in fact, I'm not interested in the full path integral. I'm only interested in the log piece. So I don't have to compute the full one-loop determinant, but only the log piece, and there's a tool for that, which is called the heat kernel. So I'm not going to explain how this is done in detail, but this is a fairly standard tool. The logic is that all you need to know is the kinetic operator of your field of mass m, and using some well-known tricks, you can express the contribution to the log term using this, what's called the Seeley-DeWitt coefficient, A4. For the fields of interest here, they will couple to GR plus Maxwell theory, and so the result will be a function of the curvature of the background. So this is the Euler density, the Weil square, Riemann square, and here is a Maxwell field, flux. And so this is called the local contribution. In addition, you have to worry about zero modes. I would not have much to say here about zero modes. They're hard to compute in general. We know them on some simple spaces like empty ADS or ADS2 times the Riemann surface. But what's important is that in the cases that this is understood, the zero modes are independent of any continuous parameters. While as these curvature things here and the background flux in general are functions of things like angular momentum or mass and things like this. Okay. So here's how it works for a massive scalar. We'll be interested, as I said, in 4D Einstein-Maxwell theory in Euclidean signature. So I have a Ricci scalar, a Maxwell term, and a cosmological constant. And on it, I will put a free scalar field of mass m and charge q. And then if you run this machine of the heat kernel, you can compute explicitly these coefficients A, E, C, B1, and B2 as a function of the masses and the charge. And for those of you who know conformal anomalies, they will not be surprised maybe to see that this A and C are exactly the conformal anomaly for a scalar field. So that's why essentially they're independent of the mass, whereas these two things are functions of the continuous parameter. Okay, so we turned the crank and we did all of this for fields of spin up to 2, massive and massless. Some of these things are new. They were not done for some reason in the literature on asymptotically ADS Einstein-Maxwell solutions, but we did our homework. There's some subtle aspects here. You have to worry about whether the field that you're studying is massless or not. If it's massless, you have to introduce a ghost, and if it's massive, there is a Stuckelberg friend of it. Anyway, so here are these explicit results. And now, if you have some favorite EFT in ADS, in an asymptotically ADS background, you need to inform me what's the metric of the background, the Maxwell field. Then I'll compute these curvature invariants, shove in the numbers corresponding to your fields in your EFT, and then I'll get the coefficient of the log. So it's an algorithmic thing from here on. But before we compute in the modern era, we should bootstrap, right? That's the logic. So we did also that. So it's not clear how out of these numbers, which are functions of the masses and charges, which I'm not writing here, but we also have this B2 quantities, how out of them you can assemble something that's just 1/2 or 1/4. And in fact, you can take two examples, which are precisely the dual. So the first example is the dual of this squashing of the sphere. It's an explicit metric. It's called ADS Taub-Nut, and this is the supersymmetric version of the metric. The details are not important, except that it's an explicit background, which is a function in which the Maxwell field and the metric are functions of this parameter B, which is a continuous parameter. And then you can also do a Euclidean version of the Reissner-Nordström black hole, where again I have an explicit metric, a magnetic field, an electric field, and a parameter Q. These are BPS backgrounds with continuous parameters. And somehow, when you compute the on-shell action of these things, as well as these log n terms, you should find that the coefficient of log n is independent of those parameters. And the only way that it can work for any EFT on ADS is if the total contribution of these C, B1, and B2 coefficient is equal to 0. So your EFT has to be super finely tuned if you want this to happen. Okay, so this is, I'm not specifying an EFT, I'm just saying that if you want a simple rational number as a coefficient, this has to happen. And we were wondering how does this happen, and we went and studied an example, which is 11D supergravity compactified down to 4D on a sphere. This is really not a standard EFT, and actually that's how it works. The reason it is not an EFT is that the radius of this sphere, the scale of the sphere, is as big as the scale of the ADS. So from the perspective of ADS, I have infinitely many fields with the Kaluza-Klein modes on the internal space. These modes can be organized into multiplets, and so here I'm giving you the SO8 quantum numbers. They're dimensions of the dual CFT operators, which are related to the masses of the fields, and here's the spin. And so now I have to use this information and my table of Sealy the with coefficients and assemble all of this and compute. And what happens is a little bit of a miracle, exactly what this bootstrappy argument told us should happen happens. And it happens order by order in this KK tower. In addition, so the whole contribution from these terms, individually they're non-zero, but they add up to 0. Thanks. And the only thing that's left is this AE, which in a wildly non-pedagogical manner I did not emphasize, is the coefficient of the Euler density. So when you integrate this term over the manifold, you'll get the Euler number. So this is the way that you find something that's independent of the continuous parameters. Because of course the Euler number should be independent of the continuous parameters. Okay? And we did that. And for this A, I have infinitely many fields. And for each member of these multiplets, I get a non-zero answer. So I don't find 0, I find this infinite sum. So this infinite sum is the outcome of assembling all of these modes. And we should compute this sum, regulate it somehow, but I don't know how. Because it's a scheme-dependent thing to do. So, but what we have in the QFT is infinitely many answers for path integrals at large n. So I can choose one of these answers, fix sigma, and then see if that's consistent with all other answers. And if you do that, you find that sigma should be minus 1/3, and then you find a result, which is that the coefficient of the log n term for any 3-manifold, for ABGM on any 3-manifold delta m, which is a boundary of some asymptotically ADS4 space, is given by this very, very simple formula.
I assume that if you do zeta function regularization, you come with the minus 1/3.
You assume correctly, yes. We can talk about it later, yes. Yeah, we should talk about anyway, so this whole thing that I've told you about can be done over and over again for as many examples for which we have the full KK tower, the spectrum of the full KK tower, the masses, and we did that for all examples we could think of, and it works in the same way. So we find agreement with the dual CFT results for other models. Okay, so here is Milan Kundera for you. So out of this analysis, we started thinking, well, this is a very finely tuned problem. Most EFTs in ADS will lead to the coefficient of these log terms that are functions of continuous variables. If things in ADS are UV complete and holographic, this implies something for the dual CFT, which is pretty exotic. So here I'm phrasing things in terms of n, but you can reorganize things in terms of lambda if you have a coupling. Thanks. The point is that if you have finitely many fields in ADS, unlike these KK non-scale separated examples, you will have a problem, because generically, for a generic spectrum, for not finely tuned spectra, if you just randomly write down fields in ADS, a finite number of them, you'll find that the coefficient of this log n term of the putative dual CFT is a function of continuous parameters, which implies that integrated 2-point functions and 3-point functions in that CFT have log n terms. In 3D, I don't have anomalies, so I don't really know how to obtain such log n terms or log lambda terms. So that's an argument, not a proof, but an argument that suggests that such things should not happen, which means that every EFT in ADS, UV complete, is constrained to obey this very, very specific condition, that the masses and the charges of these fields in your EFT should add up in this very specific way. So this makes me use the S word. So this looks like a swampland criteria for UV completion in ADS, and maybe this is interesting for people who care about scale-separated vacua in ADS, which have finitely many such fields. Okay, I have 1 minute, or -1. You can do now, all we did was using supersymmetry However, the results we obtained on the gravity side actually do not rely on the supersymmetry of the background. They can be applied for other asymptotic ADS background. So, for instance, you can do ADS Schwarzschild, and you can compute the log n term correction to the entropy. We can also compute this n to the 1/2 in a way that I don't have the time to explain now. You can also compute the things that Ellie was clickety-click speaking about. So thermal one-point functions, in this case of the energy momentum tensor, and because in this ADS4 background chi is equal to 0, the Euler number is equal to 0, you'll get no log n term. Okay, this is what I told you about. I told you that we can compute, at least at large n, path integrals of certain SUSY QFTs on compact manifolds. And I told you how the log n term in these expressions can be computed from the dual gravitational theory. This helps us or constrains black hole thermodynamics in some ways, and maybe teaches us something more general about EFTs in ADS. And we even managed to compute some thermal stuff, which is cool. What I didn't tell you about is that we can do this for a large class of other CFTs with various internal manifolds in other dimensions also. And there's some open questions. These logs look very simple. I told you how to compute them, but I didn't really tell you why the result is so simple, so this begs an explanation. And maybe this is teaching us something about string or M theory. Maybe there's something like an OSV in ADS. And finally, this last thing which I mentioned seems more general than these examples that I told you and may be interesting to explore. Thanks a lot.
Question?
Are there multi-centered black hole solutions in asymptotically ADS4 that could contribute to the index?
People have tried to construct multi-centered ADS4 backgrounds. To the best of my knowledge, the only attempts have been inconclusive, to be generous. Yeah, there's no fully back-reacted, two-centered black hole in ADS. So, yeah, I don't have anything to say more than that.
So if I understood correctly, if you have a very heavy scalar in ADS, whereas for normal quantities, I can just ignore it from the EFT point of view. Here, you need to know it's there, otherwise you would not count it for the logarithmic coefficient.
I think the principle that I've been using here, following my nose and the shock sense guidance, is that you first fix the cutoff scale and then do the calculation. So if you wish, you can fix a cutoff scale, have finitely many fields, find this inconsistency that I was advocating for, and then you should be saying, oh, that's either my theory is UV bad in some way, or my initial fixing of the cutoff is somehow wrong.
But is it consistent with integrating out something, like
Yeah,
lowering
so,
the cutoff?
for instance, what you can ask in these examples, which I don't have the time to talk to, and also the calculation is very hard, so we haven't done it in the bulk, but you can imagine how it's going to work, is that in the type 2a limit of ABGM, you have a log lambda term. That log lambda term should somehow become this log n as we integrate in the kk tower from the S1. Yeah. Vasco is going to ask a question.
So you have this magnificent minus a third result for a infinite sum that you are defining through holography. Is there any way to get like more results that mathematicians would be interested? Like, can you imagine like getting similar things from other ADS50 examples that can teach you something about something?
I don't have a good answer. I mean, I'm not very interested in the question because this is some scheme dependence.
So, okay, can you explain the scheme design?
Well, I mean, I don't know how to explain it. It's not a QFT class, right? I mean, it's one thing that I cannot fix, and so I need to kill a divergence somehow with the, I don't know, what's the regularization scheme in 11D supergravity? I don't know. This is not an EFT, right? This is infinitely many fields that I'm resumming somehow.
Okay.
But what is true is that on all examples, you will find a divergence like this simply because the scale of this internal manifold is of the order of the ADS scale. So you will always be faced with a problem like this, that one number, this regulated sum, cannot be computed with first principle calculations, at least with the meta time using.
So do you have any idea, like, I mean, about different dimensions, like 5-dimensional black holes, or like in 6 dimensions, like would you expect only type A anomaly?
Very good. So some of the things I told you about change, well, and many of the things I told you about change in ADS5, let's say. In ADS5, we don't expect a log term unless, so this Seeley-DeWitt coefficients in odd dimensions contribute 0. So the only thing that can contribute are the 0 modes. And on the examples that have been studied, there are no 0 modes. And also from the superconformal index, let's say, at large n, there's evidence that there's no log n term unless you change the gauge group from SUN to SUN mod ZN and things like this. Yeah, so there's no local contribution of a log type in ADS5. In ADS6, I would expect that there is a similar story, but this Seeley-DeWitt analysis is much more nasty, and so yeah, we haven't done it.
But you don't know if it's just a type A.
I mean, I wouldn't call this anomaly, because B1 and B2, these things are not anomalies, right? I don't know, maybe the language I'm using is not the language that you're using. These are anomalies, obviously, but these are not.
Okay, we should probably
Thank
come
you.
to a halt. Thank
Since
you very
I'm the
much.
last speaker, I want to thank the organizers, which everyone did. But also there are some people running around with microphones. I don't know them, but they've been doing an amazing job. And I'm sure there's other people outside of this room who contributed a lot. So thank you all. I had an amazing week, and I'm sure we all did. Thanks.